Okay, good morning, everybody, or good afternoon. All right, so what I want you to do is there's an available link on the lecture notes page, as well as you can see it up here. I'm going to be following along and showing you the same thing. And what we're going to do is we're going to we're going to complete a doubly linked list. We're going to see another makefile example where we're aggregating classes and seeing which ones we should template and which ones when we don't template and how we include it. And then we're going to work on two more data structures that aggregate off of singly and doubly linked lists called stacks and queues. So if you go to this link, you will see that you should check out, I'm putting everything that's going to be graded for next week. So today's lecture code, Tuesday's lecture code, and then coding challenge 4 are all going to be under the same branch. So that's going to be CC04. So you see that's what's going on. If you haven't started that yet, you can do this here. Check out -B CC04. And then create a folder, lec08. And then what you're going to do is you're going to run this wget command. And the wget command is going to get a script. So just like last time, you're going to download one file, run the script, and that's going to set up everything else for you. So the way to do this, you run this wget command. And so this raw GitHub user content removes all of the HTML from what you would normally see on there. So it's just downloading the pure code. And SP21 CSE 20312 lecture 08/setup.sh. And so that's what's going to successfully happen when you run that command. And so now what's going to happen is if you I see that test folder. So you run that command. What error 4, no 4 not found? I must have mistyped something. There we go. So that's what's going to happen when it's successful, and you're going to see this setup.sh command. The next command you can see at the bottom, chmod a+rx setup.sh, and what that's going to allow you to do is to enable, just like you've done before in other test scripts, being able to actually run the script. So when you run it with setup.sh, it's going to start downloading all these files. It's going to run just like that. And you'll know if it was successful if you do ls-* and it looks like this. So I'll give you all a moment to run the script so you can download those files. So while you're doing that, the first thing we're going to do today is we're actually going to go through the process of inserting a node into the back of a doubly linked list. We're actually going to write that code together and then watch as we compile. And then what we're going to do is we're going to start playing around with destructors and produce memory map errors so that way you can recognize why it is that these things happen. All right, so everybody give me a thumbs up when you have the script run in your code download. Okay, lots of thumbs up, outstanding. All right, so I'll stop buying a little bit of my time there. So one last thing, as I'm going to be working through it, we're going to be coding together. So just as a reminder, I don't want you to think of this as pure just copy and paste. A great example from last week's lecture was when I wrote up that assignment operator for a node pointer and got lots of questions and we had a really good discussion. If you're confused as to what it is that I've done, please don't hesitate to raise your hand. For those of you who are on Zoom, please all of you are welcome to ask a question in the Slack, and I'll continue to monitor it as I go through class. And so here's all the stuff I've been talking about. So what I would like you to do first is I want you to go into the file include dll-list.h and then go to line 81. So here I have it in FileZilla. So you would go into lec08. I have a test folder. If you go to include, and then DLL list. And let me scroll in a little bit. So we covered a lot of this before, and what we're going to do today is we're going to go to here. So what you should see is a method that says void insert, and we have const t ampersand value. We're passing, we can create constant values, and we can call by reference. So what we're going to do is we are going to go through step by step and learn how it is that we actually insert into a doubly linked list. So what's going on here is we're going to write this together. These are the first few lines. We're going to create a temporary node. And then the first case we're going to account for is if the doubly linked list is empty. And in the diagram, what this represents is we have two node pointers, head and tail. If they are both null, it's empty. So we have a method that we discussed last week is empty. And if they're both null, it will return true. So in this case, what's going to happen is this line of code here will create a temporary node pointer, and the new keyword allocates memory on the data heap. So we have an address, we have the value itself, we have each node has a previous and next pointer. And then we're going to check if it's empty, and here it's null and null, so it is empty. And then what's going to happen is we're going to set head to point to the same location in memory as temp, and we're going to do the same thing for tail. Does that make sense so far? So let's write that together. So inside, I want you to go into here, and I want you to say node t star temp equals new node. You have to template it like this, and in the constructor, which we went over last week, we pass the value. In fact, let me zoom in a little bit so everybody can see. So then the next thing I would like you to do is we're going to say if is empty. So in this case, in the class, it's uppercase I and uppercase E. And inside of that, we're going to say head is equal to temp, and tail is equal to temp. So far, we've accounted for the empty case. Hold on for a second. Mute all. Okay, so everybody on there should now be able to hear me. All right, so we create the node, and we can see on the right that we have a new node. And then I check if it's empty. That's not true because we are now have a value that we're actually pointing to. And then what we're going to do is we're going to create two pointers. The first one is going to be called previous. And right now, that's pointing nowhere. And we see that because it's right now it's pointing to a question mark. Then I'm going to create another one called cur. And cur is going to point to the same location as the head node. And what's going to happen is you're going to see this pattern where we're going to be walking along. So what's going to happen is cur is going to be one step ahead, then previous is going to catch, and we're going to keep going. And what's going to happen is because it's a doubly linked list, we're going to be pointing in two different locations. We want to keep track. In the event that, and you're going to be doing this on Coding Challenge 4, you're going to be inserting in the middle when doing a sorted doubly linked list. So what's going to happen is cur is not equal to null. So while it's not equal to null, meaning we have another node, we are going to iterate through. So what you're going to see up here when I see previous is equal to cur, you're going to see this pointer point here. And then we have this line here, cur is equal to cur next. So you're going to see cur is pointing here, and that's this node. And then next is going to point to that location. And so because that node is pointing to null, now cur is pointing to null. And so when we get up to this while loop, what we're going to see is that now it's null. We don't iterate anymore. And now it's going to jump down here to this previous next is equal to temp. What that means is that the previous pointer is pointing to this node in the heap, and then next is here, and it's going to point to that location that temp is pointing to. So this is temp. So now what you can see here with this arrow is it's now pointing there. The next line of code is a little more confusing to students initially when they're getting used to pointers, so I'm going to walk you through it. The next line of code says previous arrow next arrow previous equals temp. So let's see what that means. So we go here, and what I have circled in red is all the important information you need to understand this. Previous, let me make that a little bigger. So previous is pointing to this node. That node, now that we've dereferenced it, has its own internal pointer called next, which is pointing to a different location in the data heap, right? So now we've dereferenced it again, and that's going to be this particular node's previous pointer, which is currently pointing to null. What we're now going to say is equal to previous. What that means is this is the initial previous, so now it's going to point here. So previous, arrow, next, arrow, previous, and on the right-hand side, when it's an assignment operator, it's going to assign where the normal variable name is. Does that make sense to everybody? Yes. What? Correct, it's currently pointing to null. That means we don't have it's not pointing anywhere, so now I'm updating it. So previous, arrow, next, arrow, previous is the node pointer that's pointing to a location, and now we're setting where it's pointing to. Yes. Yeah, so previous, just this, is pointing here to this node, right? When I dereference it, now I'm getting a value inside this node. When I say next, that's now this pointer here. And then that value, when I dereference it, is pointing to this node. So then that node contains another private member, previous, which is now currently pointing to null, as was pointed out here. And what I'm doing is I'm now updating it here. So the question is, so it's sort of moving in a loop. So a doubly linked list is kind of like a loop in that we are going to have this one pointing here and this previous pointing here. And the doubly linked list allows us to traverse in both directions. So when I update that and run the code, we're now going to see that the last thing I do is I update tail pointer to point at the last node. And then when I go out of scope, previous and cur are going to go away. And now what we have here is a doubly linked list linked in the forward and reverse directions. Well, now I'm going to do the same thing with a third insert. I create the node. It's not empty. Previous is null. Cur is now pointing at the head. So while cur is not null, we're now going to have previous catch up. So you now see that cur and previous are pointing at the same node. Cur is going to go to cur next, which again, to reemphasize, cur is pointing here. Then I dereference it, so I go to the private member of the node, and next is pointing here. So you're now going to see that cur is going to point here. And that's exactly what happens. We go up, cur is still not null. Previous is going to point to the same location as cur, and cur next is going to point to where that node is pointing, which is null. And that's good. That's what we want. We've now found the end of the list. So again, previous, so here we go, cur is not null. Then previous next is equal to temp. So now we're pointing to the node that we've created. Previous next previous. So walking through this again, previous dereference. Now it's pointing to this location, dereference, previous now points here. So now we're going to see that tail is going to point to here, and we have a previous pointing back to this node. And so when it goes out of scope, we now have 3 nodes in the order in which we inserted them. So let's walk through and write the rest of this code together, and then I'll open and see if there's any further questions. So then this is going to be an else case. So the first step, we're going to create 2 node pointers. So it's going to be node T star previous is equal to null. And then node t star cur is equal to the head pointer. So now while we traverse, what's going to happen is we're going to say while cur does not equal null, like that. So then we're going to do this walking where previous is going to be equal to cur, and cur is going to be equal to cur next. If I can actually type right. So now that's our little walking procedure. So now what we're going to do is we're going to sum up the last part. We're going to say previous next. So previous is pointing to the last valid node in the linked list. Yes. I'm sorry, can you speak up? Cur, yes. What about it? Correct. Yes, that's exactly what's going on. Awesome. That's a sign that they're all putting all the pieces together, all the void pointers, all that stuff about stacks and heaps. It's all now coming together in the doubly linked list. So cur is now pointing to the next location. When we get to null, that means the cur is past the linked list and previous is at the last element in the linked list, which is why we say previous next is going to point to that temporary node that we created, because we now want that to be part of our linked list. So previous next, tell me where the next element is, because previous is at the end of the linked list, is equal to temp. And then after that, let me scroll down a little further so everybody can see. Next, we say previous, next, previous. That's going to be now at the current location. So I could say temp previous, that's another way of doing it, or I could say previous, next, previous. The reason I'm presenting it this way is because I want you to all think about how pointers are actually working. So even though it's a little more complex to code, it'll hopefully strengthen your knowledge of pointers, so that way when you encounter them later in the course, it'll be easier for you to implement. So now we have one last line. We have to make sure that the tail is pointing. So we have previous, next. And then when everything goes out of scope, then our doubly linked list is complete. All right, does anybody have any other questions about this? Okay, I don't see anything in this Slack either so far. So now I'm going to save this and update it. Next, I want to introduce a method that's already in this file called push front. And what push front does, and we're actually going to use this later when we discuss stacks and queues, is how I would want to insert a node at the beginning of the list. And so the way this is going to work is I'm going to, again, create a temporary node. And then I'm going to say temp next is equal to head. So I'm moving the head over. And this can be anything. This could either be null or another node. Right now, what's going to happen is I'm setting my new node to point to the current head pointer. And then what I'm going to do is I'm going to update head equal to temp, like so. So now we see that the line has been updated. And then the last thing I'm going to do is I'm going to say, well, if tail is equal to null, that means the list was initially empty. So now I'm going to update that value. If it's not null, that means there's another node in the list and the tail should still be pointing at that node. Does that make sense? So that's how we've got this put together. And now I want to do push back, which is the other thing I alluded to a little earlier. With push back, let's say I have some sort of node here and it's currently pointing to tail. Tail is currently pointing at it. So first I check to see if it's empty. If it's empty, I'm just going to call insert. So that way we can put it in the beginning and take care of all that other stuff. But in this case, we're not empty. So what we're going to do is we are going to create the new node. Then what I'm going to do, temp previous, which is here. So this is temp. Previous, I'm going to want it to point to the previous tail node, because I'm going to create this link structure. And then the last thing I'm going to do is I'm going to move tail to point here. So the way we do that, we say temp previous is equal to tail, and we see that the arrows up, and then tail next is going to point to temp because that is going to become our new tail node, like so. And then finally, I'm going to update the tail pointer to point here. Does anybody have any questions about that? Oh, no. Yeah, I see there's some chat, a typing going on in the chat. When it's done, I'll address the question. All right, last thing, I'm going to show you this friend operator. So let me go here, down here at the bottom, so that way you can see what's going on. So in a friend operator, what I'm doing is I'm using this same kind of walking with the cur. And so what I'm going to do is I'm going to have cur point at the head here. And so what's going on here is we have const doubly linked list call by reference. So if this doubly linked list is getting significantly large, this call by reference becomes beneficial because we're not making a complete copy of the doubly linked list, just pointing to where it is in memory. So the question is, so push front is inserting the node at the beginning of the list, and push back is inserting the node at the end of the list. That is absolutely right. It's 100% correct. So first, I'm going to say if the list is empty, I'm just going to print out the list is empty. Otherwise, I'm going to have cur point at head. And then what's going to happen is I'm going to keep going until I hit cur is equal to null. That means I've reached the end of the doubly linked list. At each point, cur arrow data is going to give me the data that's allocated in that particular node. So we're going to print those all out in a row. And then what I do is I just have this little arrow to indicate that it's a linked list. So deletion. So delete, what I'm going to do is I'm going to create 3 node pointers. And those 3 node pointers are going to help me keep track of the previous, the cur, and what I'm going to call temp. Temp is going to be the one that when we identify it, that's the node we're going to delete. So let me show you how this works. I'm going to create 3 nodes. I'm sorry, I'm moving this over here. So I have 3 node pointers, previous, cur, and temp. We are not empty. And so in this case, I'm going to say if target is equal to head data. So in this case, my target is 12, and I want to delete the head node. So how do we do this? First, I'm going to check to see if head and tail are the same. In this case, they're not. So we're going to skip past this if statement. And now what we're going to do is we're going to say temp is going to point to the head node because that's the one I want to delete. But I also have to ensure that I can figure out where all these other nodes are. So what's going to happen is we're going to say head is equal to head next. So right now it's pointing to this node, and it's going to move over here. So far, so good. And now what we need to do is the current head pointer, the new head pointer needs to point to null. Nothing should be in front of it. Does that make sense? So what we're going to see is that that head previous is going to be set to null right there. And then the last part is we're going to use that free keyword that we discussed at the beginning of the semester. And the memory that's being pointed to by temp is going to no longer be in the data heap. So we move to this next line of code, and we see that it's gone. And this brings me to one of the true benefits of linked lists. In a linked list, you are only using the memory that you need to use. In a vector, which we're going to learn about next week, you have a scenario where you could potentially have twice as much memory as you need. So while vectors have direct access when you use the .at method or use the brackets, the trade-off is more memory. With linked lists, in order to get all the information, you have to traverse through all of the nodes. However, the benefit is reduced memory consumption. So here we can get rid of things when we are no longer done with them. So the question here we have, why does our example have node templated, but okay, so that's because I ran out of time, but we need to template that. But yes, so here's the actual code for delete. So here they're all templated. So in this case, they're like so. The last year I had the node as a private member of the class, so I've missed that. Did that address your question, Natalie? All right, good deal. Okay, so now let me stick to this. And so what we've done here is now we have one case where we have one node and it's our target. So we're going to go through. We're not empty. We've created our 3 new nodes. We're not empty. Target is equal to head data, so target is 10 and the data there is 10. Now we have the case where head is equal to tail. We only have one node in the doubly linked list. So what's going to happen is temp's going to be equal to head. Then I'm going to set the node pointers. Head is going to be equal to null, and tail is going to be equal to null, which means that we now know that we're going to want an empty doubly linked list. Then I'm going to free the memory at temp. And now that memory is gone, and we now know that we have a free and empty doubly linked list. So here another case is, if it's empty, we see that this particular if statement will ensure that we don't have any issues. We don't unintentionally try to delete memory that we don't have allocated. So now what I want to do is I'm going to have a non-empty delete case that's not at the head node. So it's in the middle, and we're trying to delete a specific element. So here's what's going to happen. First, I'll set previous equal to head and cur equal to head next. And the reason I know I can do this is because I have already accounted for all of the scenarios in which there are 0 or 1 nodes. So now we can say there are 2 nodes here, and I can walk through, and then what's going to happen is I'm going to keep going while cur is not null, and we're going to keep iterating through here. So now what's going to happen, let me go to the next slide here. What's going to happen is, while cur does not equal null and cur data does not equal target. So that line of code is here. We're going to keep iterating with 2 cases. 1, that the list is not empty, and 2, that the element that we're looking for hasn't been found yet. So if we find the element, that means that we can, that we stop the iteration. So then we keep doing this little walking with previous and cur. If cur does not equal null after that iteration, that means we did not get to the end of the doubly linked list, which means we found the element we wanted to delete. So from here, we go through the process of setting everything up. So I'm going to show this in animation. So here what's going to happen is I'm going to iterate through. And so what's happening is cur is pointing at 10. I'm going to set temp equal to cur. And now here's why we need previous and cur. Because I am going to have the next element that's after cur needs to be linked to the previous element. So the element currently containing 12 needs to be linked to 8. So we're freeing 10, but we have to preserve the doubly linked list. So what's going to happen is, if cur is equal to tail, then I would set tail here. So if in this case, if we were finding 8, we'd want to get rid of that. Otherwise, what's going to happen is, I am now going to say previous next is equal to cur next. So here's what this means. Previous dereference next is equal to cur dereference next. Cur next is currently pointing here. So what that means is I want this value to point here. So you can see that I'm now circumventing the other node. My goal is to get rid of it. So now that I have previous next previous, I can now point this here to previous, and now I have the 2 nodes on the opposite side of the one I wanted to delete, pointing at each other, and neither of them are pointing at that current node. So we see that that's been updated, and now we have this result. So what this allows us to do is, again, free the memory that we are not using. And so now I'm going to go through an animation, an example where I'm deleting the tail node. So here I set them up again. Previous is head, cur is head next. I do my walking. I've found that cur now is equal to the target 8. And then if cur is not null, that means we want to free our elements. So temp is going to point to the same place as cur. Cur is equal to tail. So what you're going to see is that tail is now going to point to the previous value, which is at 10. Then previous next is equal to cur next. So now in this case, previous is at 10. And by saying cur next, it's actually updating it to null. So this condition has met one of the other requirements of the doubly linked list, which is that we are going to have to point to null at the last element. Then we free temp. This case, previous next is equal to null, so we're not going to update anything. Then previous incur go out of scope at the end. So 20 is not here. So we're going to do the same thing. And what's going to happen is we're going to keep going. And then when cur gets to the end of the list, this means that we've tried to delete an element that's not in there. So if cur is equal to null, we return false to let the user know that we did not successfully delete anything because it's not in the list. So another thing is the destructor. So in the destructor, I'm going to show you a line of code here that I'm actually going to uncomment after we compile everything. So here in the destructor, notice how I have delete head, but that I have delete tail commented out. The reason why is we're going to produce a memory map error, and we're going to see with our understanding of void pointers, the stack and the heap, memory allocation, nodes, and classes, how it is that we can avoid that and identify that as an issue. So what's going on here is that when you call delete head in the doubly linked list destructor, that is going to call the destructor for the nodes. The node inside here, which we wrote last time, deletes next. So we see that head is going to point to next. And now what happens when we do it this way is we are actually going to use recursion to go all the way to the end of the doubly linked list. And so this happens because we call delete next in the first node, then that node calls it delete next there, and then that node calls delete next, and we hit null. Once we hit null, then we're going to go back up the call instruction stack, and each time it's going to free a node. And then we delete the pointers. So why don't we call delete tail? The reason why is because tail is now no longer pointing at any memory. So if I call delete tail, it's going to try to look for places in memory that are no longer there. They're no longer allocated per the operating system. So what will happen, and we'll see this in a moment, is that we will get we'll get that big memory map trace, and I'm going to show you how we can prove it. So in the doubly linked list, I'm going to scroll down and I'm going to show you a method that I've written in here called print addresses. And so in print addresses, it's going to print the value of this. Then it's going to print the locations of the head and tail pointers, or where it's pointing in memory. And then I'm going to use that same iteration process, and I'm going to print out just cur. So cur is a register with a pointer, so it's going to print out the locations of the base address of all the nodes in the doubly linked list. And we see here cur is equal to cur next allows us to be able to continue to iterate through. Yes? So it depends on the contents of the node. So here, all of this points to the base address of the class. Head is pointing to the initial node in the linked list, and tail is pointing to the last one. Sometimes they can be pointing to null, sometimes they can be both pointing to the same one. And I have an animation that's going to make all of this clear that we're going to go over in a little bit. So at this point, what I'm going to be able to do is I'm going to be able to, now that you have this updated, I hope I didn't, okay, so make DLL list test. And we're going to see that's going to compile. And then when I run it, we're going to have student in the address, then I have the arrow, then I have the next student in the next address, and then we have the next student in the next address. So me and Professor Bowie, we live right down the street from each other in Nowhere, Indiana. And then I can use this contains method, and it's going to go through and see if that node is there. And then I print the list at the end. And here at the bottom, we see I have two lists. Now let me show you what DLL list test actually says. So we went over this last week, but I want to review. So here I've created three students, and then I created the list, stu1, stu2, and stu3. And then I had this method contains, where I go through and I use the comparator and student to be able to look everything up. And then I used the assignment operator, and then I deleted stu2 from the list. So we see at the bottom that it goes straight from Brian Kelly to Peter Bowie, that I have been removed from that list because that's the one that I passed. And we saw that in the deletion. Now here's the interesting thing. Here's what I want you to pick up from this method that I have here. So here's what I have highlighted. This pointer contains the address, the initial address. It's different from the head and tail. So head is pointing to a location. One list is pointing to DC 300, and here is DC 3 Foxtrot 0. So they are pointing to different locations because they are different linked lists. And then tail here is pointing to, it ends with Charlie 3 Alpha 0. But we see here that head matches with the first element in the linked list when we're printing the elements. And tail matches the end here. So when I delete one, we see that head and tail are going to match the two remaining elements. So we see that this works. Does that make sense to everybody? I don't see any questions in the Slack either. So what I'm going to do next is I'm going to go to my doubly linked list, and I'm going to uncomment that delete tail. Now, one piece of advice is you're going to get more and more used to working with templates, is that when you're compiling, because we're not creating an object file with a template, sometimes it doesn't get picked up by the compiler. So whenever I do write code with templates, I always run make clean, and then I compile again. So what's going to happen is we make DLL test, and it's going to go through and compile everything. And then when I run it this time, it's going to run, but as you see here, we now get this memory map. And we see that double free or corruption. That's the error. It runs and does everything. It prints everything as we expect, but because of the destructors are called abstractly, that's why we get that issue. Does that make sense to everybody? Awesome. All right, so run make clean, and now I'm going to fix that and comment it again. And then I'm going to run those same three because I want to make sure that my update, yep, there we go. Okay, so the next thing I want to go over is, and this is going to address your question in detail about precisely what's happening. So here's how the doubly linked list is arranged on the data heap. So now we're taking what we've learned abstractly and we're now putting it physically into the system. So when I called the assignment operator, we have two pointers that are this for list 1 and list 2. List 1 is pointing to the location of the head node. And then the head node is pointing to the first. And then next is pointing here. And then next is pointing here. We see that this node is not pointing anywhere because it's null. And then tail is going to point here. And then we have the exact same thing going on up here. So when I called delete, what happened is it created those three pointers, previous, cur, and temp. And then initially, cur is going to point to this node. And then I iterate, previous is going to point to that same node. And then we're going to do that walk again. So here's that walking process. And now we found Morrison. We got to delete Dr. Morrison. His coding challenges are too hard. We got to get rid of him. So we're going to delete him from the list. Okay, a few of you nodded a little too hard. Okay, okay, so now we've found it. And now we're going to do that same process. We're going to update the previous and the next nodes. So what we want to do is we want to get Professor Bowie's previous to point to Brian Kelly. And we want Brian Kelly's next node to point to Professor Bowie. So now we're going to update that. We have temp, that's going to point to me. We're getting rid of Dr. Morrison. And then we see that the next node is now pointing to Professor Bowie. Professor Brewery's previous is now pointing to Coach Kelly, that we call free temp, and now my node is gone, completely out of the memory, can be used by the computer to do anything else. Did that address your question? Does anybody have any other questions about this? All right, awesome. So for free, cur, and previous, oh, that's right, it goes out of scope. So now what I want to do is I want to kind of go over again this idea of input and output operators in the context of aggregated classes, but will then be put into a template. So what I would like you to do is I want you to go to the source folder and then open up line.cpp. So line.cpp is a file that we've found before when we were talking about aggregated classes, where we have a point class and it builds off a line class. And we're gonna write the first 4 lines of code here. And then what you'll see on the screen is I have 2 lines deliberately commented out. What I'm gonna do is I'm gonna write those 2 lines of code, show you the issue that comes up, and then the solution is gonna be those last 2 lines, okay? So once you have this here, so let me go into FileZilla and open it. So I'm in the source folder and I'm gonna go to line.cpp. And so if you scroll down to line 56, you'll see this in-class work begins here. And that's part 2, not part 3, I apologize. So the first thing we're gonna do is we are going to use coordinate. So coordinate was a type def double. So coordinate, and so let me actually, I'm gonna zoom in and scroll up just a little bit so everybody in class can see. And so I'm gonna call them x1, x2, y1, and y2, because I'm gonna create 2 points. Like so. And then I'm gonna say input, because that's my I stream. I'm gonna say x1, y1, x2, and y2. And then I'm gonna create 2 points using that data. So I'm gonna say point, temp origin, and then I'm gonna say x1, comma, y1. And then I'm gonna say, and this should be point origin. And then I'm gonna do the same thing, we're gonna call it point temp destin. And it's gonna be x2 and y2. And so just save for now, and then update. And then what I want you to do is we're going to go to the make file. So go up 1 level, and while it's retrieving the directory, what we're gonna do is we're actually going to think about it, because we're gonna have classes for a test file. We're gonna have point, line, node, and doubly linked list. And what we're gonna think about is, which objects do we want to include and which ones do we not want to include? So if you go to the make file, scroll down to line 54. So I want to do the make file so that way we can compile this code and then I can show you some of the issues that come up. So everyone give me a thumbs up when you're at line 54. Okay, lots of thumbs up, outstanding. So in this make file, in order to compile that first doubly linked list test, see I have address, student, doubly linked list test, and then I create all these object files. So we're gonna do the same thing. And with the first thing, we have to think through what is the hierarchy. So we have a final code, and let me just remind myself what the file is called, DLL test 2, so that is correct. So DLL test 2 is going to bring in point, line, and doubly linked list. So I'm gonna create some lines and I'm gonna put them all into the doubly linked list. So the first thing is point, line is dependent on point. So let's create the point object together. So this will just be object/point.o. And in order to do that, we need the source point.cpp. And then we create our production quality compiler flags. -C takes a C++ file and we're gonna create an object with it. All right, so Sean, I'll get to your question in a split second. And then here, we would just do the same thing. It's source point.cpp. We do -o and $ampersand, and that creates our point.o file. Then we have, I'm just gonna copy and paste here. This will be line.o, and so line, because of the way we had it set up before, is going to include from point. So by creating the object file for a point, we can then create the object file for a line. So because doubly linked list is not templated, I'm sorry, it is templated, excuse me. We can't create an object because we don't know its type until runtime. So we're not going to do that. We're not going to make one for node.h as well. So then the last thing we're going to do is we're going to create one for DLL list 2.o. So it's going to be same thing. And so let me write this with you. It's going to be DLL list test 2. So let me highlight that. Let me give you all a split second to type it up. And then I'm going to do the same thing where I replace that line.cpp with the DLL list 2, like that. The next thing we're going to do is we're going to create an object file list. So we're going to create that variable. So I would always just do DLL list 2 underscore objects :equals. And so here's the order. I always say do it from the top of the priority down to the bottom in that order. So we're going to say doubly linked list 2.o. So I would copy this. And then I would do line next because line is the previous dependency. And then point.o is the previous dependency upon that. Does anybody have any questions about why I put it in that specific order? All right, and Sean, I'll get to your question when we get back to the other line of code. So now that we have this, the last thing is we want to create our executable. And so our executable, we're going to say DLL list underscore test2. That's going to be our make command. And then we say $, and then we have DLL2 objects. And those are all the object files we need in order to be able to create the executable. The next thing we're going to do is we're going to do the same thing with the flags. -o, and then the format is you do the executable / DLL list 2, not objects. And then in order to make that, that's where you have all the object files. The next thing I'm going to do is I'm going to show you how you can actually get a program to execute immediately upon compilation. So then you would just do exe /. DLL list 2. And this file, we're reading in an input file and then being able to print everything there. So what's going to happen is I want you to put DLL list test.txt. And so here is the entire thing, and I'm going to explain what's going on in the doubly linked list 2 file while you're finishing up. So what I'm going to show you there is we have this code that's going to use the input stream. And so it's a while loop, and it's going to read in each element, and it's going to test to see if it's a valid integer, that I have a valid double, and then I'm going to use this overloaded iStream operator in order to actually read in everything with just one segment. And I'll show you what I mean in a moment. All right, so if we run and update this, I'm now going to show you this code here. So here's what's actually going on. So if I scroll down here, I've created an int, temp int, a double, and a line. And this while loop will go until we either reach the end of the file or we have an invalid input. So here I have iStream, so let me roll up here. So input stream, I've created an IF stream using the first input argument. And then it's going to read an int, a temp, double, and then temp line. This is the important part here. Because we have written an overloaded operator that we're going to finish here, I am able to do that with one, instead of having to read in .x.y, x.y, because I have overloaded it. And so that's what's going on here. And then I have created, let me scroll up here for a split second. I'm sorry, I didn't need to. I created 3 doubly linked lists. One is an integer, one's a double, one's a set of lines. And so I'm inserting the integer into the integer list, the double into the double list, and the line into the line list. And then at the end, I'm using the overloaded friend operator to print everything out. So does everybody understand where I'm going with this so far? All right, so now let's go back to doubly linked list.h where we were before. Let's go all the way down here. I'm sorry, my apologies, not there. We're going to be at line.cpp. So before it was at line 52. And so this should be x1 and x2, it should be x1, y1, x2, y2. And so Sean, that is the error you pointed out. Thank you. And so it should be x1, y1, x2, and y2. And by overloading it, we can now only just put in a line, and we can allow the C++ compiler to do all that work for us. And so what I've done here is we've created 2 points. And so this is a common student conceptual issue. So what I'm going to do is I'm going to write 2 deliberately wrong lines of code. I'm going to show you the compiler error that comes up, provided I wrote my Makefile correctly. What's going to happen here is a lot of students think, well, it's an input, it's an operator. So for read line dot origin, I can just set that equal to temp origin. And then I can do the same thing here. Readline dot destin is equal to temp destin. So I'm going to save it. And now I'm in test. You would be in lecture 08. I'll make DLL list test 2. Right? So it looks like I've done everything. And we've run it. Wait, did I update everything properly? How did that work? Oh, you know why? That's probably why. Okay, well, it worked. So we see here that I have doubly linked lists, and I have it split into data and then structure. So what's going to happen here is when I go back to DLL list 2, this file, I print everything out, and then I call the print addresses method. So I want to, again, get you this idea of thinking separately about data versus structure. So with data, I'm going through and I'm printing out all the data values. So here what I did is I read in 1, 14, negative 456, 44, and 100 into the int list. Here I have a list that I've read into double, and then I've successfully read in a line information. Then we see that we have this, we have the head and tail, and we see that head ends in 2B0, so we see that it ends there, and tail ends in 4B0, and we see that the last node there ends as well. So we can go through all of those, and regardless of how we template it, it will work. So data and structure, the doubly linked list allows us to structure whatever type of information we want to be able to perform all those tasks. Right, does anybody have any questions about what we've done? All right, so let me skip through here. We got the Makefile going on. So for the last 20 minutes of lecture, what I want to do is I want to introduce you to 2 types of data structures that build off of singly linked lists and doubly linked lists. And they're called stacks and queues. A stack is what's known as last in, first out, meaning we put elements into a list, but we can only access the first element. And there are lots of algorithms that take advantages of this last in, first out to be able to minimize tasks. One we're going to go over is what's known as the Towers of Hanoi problem. So with the stack, you can actually see what the C++ template libraries are built off of. So let me move this down here. So if you type in, so if we use Vim, and you can actually do this too, user include C++, and the version we have is 4.8.5, and I see bits, and then I'm going to do stl_stack, because that's the one we're going to see first. And it has all the information about how it's built. And you can see, first of all, they comment it like crazy. We see how if not defined and defined, just like we've learned. And then we learned about namespaces, and this is a reason why that namespaces can be complicated, because they keep getting added in different versions. And we can scroll down here and see all of the information. Type defs, we've learned about that. We have else if, const. You see how they use const all the time, just like we've learned. And if I scroll down far enough, I think I might have zoomed past it in one of the comments. But a stack is built off of a singly linked list. So that's how it stores all the information. So in order to do that, what I have done, if you look in singly linked list.h, is I wrote a method called popFront. And what that does is just removes the element from the front of the singly linked list. And we can think of it, flip this way, now the singly linked list is at the top. So the next thing I want to do is I wrote another method in the singly linked list called front that accesses the data in that node and returns a copy. A stack and also a queue should be able to get copies of the front for a stack and the front and the back for a queue, but only those elements. So we see here head data. I've dereferenced the head pointer, so I'm pointing to that specific node. I get the data and I return a copy. So now what I want to do is I want to show you a class stack that you have downloaded here in the include folder, and it's in stack.h. In stack.h, it has a private member of a singly linked list. It also has two other private members, maxlen and stack size. This allows me to check and maintain the maximum length that I want. So for some reason, I don't want a singly linked list over 100 nodes. I can hard code that when I call my constructor. And likewise, we're going to keep track of the stack size. So here, what I've done in the constructor, because it's templated, I have the constructor in the .h file. And I want you to notice a little trick that I've done here. So I have unsigned in maxlen. And what I've done is I've passed -1. So I mentioned this in a lab, but who here has played the video game Civilization? Okay, so several people. And you're probably familiar with the Gandhi error. And the short version of the Gandhi error is this. You get to play and be real world leaders in this game, and you're trying to build either democracy or some sort of society. And Gandhi, his aggressiveness score was 1, lowest it could possibly be. And it was stored in 8-bit register. And when you became a democracy, with whatever character you had, your aggressiveness was subtracted by 2. 1 minus 2 is -1, but it was stored as an unsigned integer. So Gandhi went from -1 to the binary representation of -1, which is all ones, 1, 1, 1, 1, 1, 1, 1, 1, which then meant his unsigned aggressiveness was 255 out of 10, which meant throughout the game, Gandhi was using nuclear weapons and bombing everybody because it was a crazy number. So what I've done here is a similar trick. I've passed -1, and now that becomes my max length. For an unsigned, I can have as much as I want. Or if I want to define the max length, I can do it in my overloaded constructor. So here I also have get methods for max size and size. I have empty that checks to see if the stack size is equal to 0. I have push, and so what I do for that singly linked list, I call that push front method. When I push it onto there, this should be const t ampersand. That's better coding practice. And then I increment the stack size. When I do pop, what I do is I remove the element from the front of the singly linked list, I decrement the stack size, and then I get top. I call that front list, so it's the front of the singly linked list. I make a copy, I return the copy here for top. So top gives me the front of this stack, and pop gives me, removes it. Okay, so there's everything I just showed you. And so I'm going to run a piece of code called wrapper stack. And what wrapper stack has done, so I've been missing all these chat questions. And so what's going on here is I put the elements in, and then in wrapper stack, I first have 10, 15, -8, and 45. So what's going to happen is I'm going to pop all the elements off, and with a stack, it's actually going to be 10, 15, -8, and 45. So when I call push and print, it's going to print the element at the top, or the value of the element at the top, and you're going to see that it's going to increment like this, and eventually as I pop and print, it's going to decrement all of them. So here in push and print, I say I'm pushing the element, I push the element, and then I call the top method to demonstrate where that is. And then pop and print, I say I'm removing the element if the stack's not empty, or if it is, then I just remove that element. So what happened, we see here, the top element is 10, 15, -8, and 45. And now when I call popping, it sees that it's 45 at the top of the stack, removes it, and now it says the top element is -8, just like we anticipated. Likewise, it goes all the way down here until it's empty. And so I put in a maximum size of 5. And now I want to show you something really quick here. So I pushed 6 elements here. Cheer, cheer for old Notre Dame. Because I set the maximum size at 5, Dame won't be able to get into the stack. Does everybody see that? So now what's going to happen is we see that pushing Dame, the top element is now Notre, because we restricted it from being able to push any of their elements. And then I iterated through and popped them all off until the stack was empty. So I want to quickly go over a common interview question. And the question is, design and draw a stack and its relationship which supports max and min values operations. So tell me what the maximum value in the stack is at any moment and the minimum value is at any moment. The reason why this is an interesting interview question is because it shows your understanding of data structures, specifically what you can access and what you can't. In a stack, you can only access the element at the top. And so therefore, it is possible that this element is simultaneously neither the max nor is it the minimum. As a result, we have to come up with another way to be able to access this information. And often they'll say, prove that the max and min operation runs in big O of 1 time. So we're going to be learning about big O of 1 next Tuesday. But basically what that means is linear. I need to be able to access it without having to iterate through all the elements in the stack. That's what that means. So that's a challenge. So let's figure out how we might solve it. So the crucial aspect is using space complexity of big O of n. What we're going to learn is that's constant, which means if you have 3 stacks, that still meets it. And we're going to understand all of that next week. But the crucial thing is we're going to have 3 different stacks. We're going to call one, that's all of the stacks. The next one is going to be just the max stack, and the other one is the min stack. So anytime we encounter a value that's less than or equal to what's on the min stack, or a value that's greater than or equal to what's on the max stack, we now update that value. And so this keeps track of the max and min at any given moment. So let's go through a step-by-step process. And I want you to bear in mind this question at the bottom, which is y greater than or equal to or less than or equal to. And so what's going to happen is we can have multiple copies of the same value. And so if I remove one of the minimum, let's say the minimum value is 2, but I have 2 copies of that data. If I remove one of them, I shouldn't lose track of the other one still being a minimum value. So we need to do both. So first, what's going to happen in this case is I'm going to insert the value 2. And when there's only one element, it is simultaneously the minimum and the maximum. Next, I would say 8. 8 is now the maximum. And notice how I've not put anything on the min stack because 8 is greater than or equal to 2. The next element I put in is 7. 7 is neither the maximum or minimum, so I do not update it at all. Then I put in 8. 8 is greater than or equal to. If I delete one copy of 8, 8 is still the maximum because another one exists. 2 is again the minimum. I put in 1. 1 is now the minimum. And then I get up to 6. So now I'm going to start popping elements off the stack and watch what happens. 6 is removed, nothing changes. What's the value of the minimum? It's 1 because I have it at the top of the min stack. What's the maximum value? It's 8 because I have it at the top of the maximum stack. So I remove 1 and watch what happens. If they're equal, I'm going to remove it, and we now see that the minimum value is 2. And that's what happens there. If I remove this value of 2, I'm going to remove one copy, but we see here that 2 is still on the minimum stack, and that in the normal stack, we have maintained the integrity of that value. Then 8 is removed. We've maintained the integrity of 8 still being the maximum. 7 removed as nothing happens. 8's popped off. We're now back to our initial case where the minimum and maximum are the same. And those are removed. So in max stack, what I've done is I have 3 private members. And I've done the same thing with the size for each of them. And in my constructor, which I can open up here in a moment, I create 3 stacks: data, max data, and min data. I create a method empty that tells me when data is empty. So if I set it correctly, when data is empty, both the max and min will be empty as well. For top, I get the top of the data. For push, here's where it gets interesting. So I do const $value as I did before. I push the value of data onto the data stack. And I say if max data is empty or the value is greater than max data dot greater than or equal to max data dot top, I push that onto the maximum stack and increment the max size. And I do the same thing for minimum. If minimum is less than or equal to the value or the minimum data stack is empty, we're going to push those elements onto that stack and increment the min size. For pop, this is first data.top is equal to max top. I print out a statement to the user max found, and I just say that's popped. And then I decrement the size of the max data. Otherwise, I check to see if it's min data. I say it's a min found, and it's popped. I remove it from the stack and do min size. And then I always decrement from data every single time. I have a function max, which just returns the element at the top of the maximum stack. And likewise, I have a minimum that gets the value at the top of the min stack. And so what that allows me to do is I am now in source maxstacksolution.cpp. I have a set of functions here that I'm just going to, first here, I'm just going to read in. So I can say I want 10 values in the stack and I have a range from 0 to 1,000. I'm going to use a random number generator to generate all these values. And then so the get inputs just is checking to make sure that what I've put in is valid integers. In main, I get those input values. You can see a benefit of calling by reference here. And then I just run srand. And so time null returns a long unsigned integer, but in C++, srand brings in an unsigned integer. So in order to prevent unnecessary bad bit shifting, I now put that in srand like so. I then create a max stack, which actually creates 3 stacks through aggregation. And so I call rand to randomly generate results. And then each time, I'm going to pop the elements off of the stack. And I'm going to print out the current top. That's the current value in the data. I'm going to print out the current max and the current min to show that it can be done instantaneously. And so here I can run max stack sol. Where I see that it's going to compile. I can say I want 10, and I want the values to be able to go up to 500. So now what happens is it generates the elements in this order randomly. And we can see that I can pop them off. And initially, the max value is 494 and 88. I found 494, and now the next smallest is there. And we keep doing the same thing until we remove all those elements. In the slides, I have a different example, 129, 155, 931, 163. It goes all the way up here. 77 is now the minimum. And we see that top is going to be 380, 931, and 77. And so I can remove all of those when I pop and iterate. Does anybody have any questions about this? The last thing I want to do in lecture is show how stacks and recursion can be used to solve the Towers of Hanoi problem. So for those of you who don't know, the Towers of Hanoi, you have a certain number of plates, and the certain number of plates, you have to move all of the plates to another stack in the same order, and you can't put a smaller plate on top of a bigger plate. So it goes like this. If the solution for 3 plates would look like so, move this over, move this over, move this over, and move this over. So it can be done in 7 moves, and we're going to use recursion to do the most efficient way to solve this problem. So we can represent a tower using a stack. We only need to know what's at the top. So what I've done here is I have a move. And when you move a plate, you have a source and you have a destination. And so what I've done is I've called tower source and tower destination by reference, and I've kept track of the number of moves so you can see that we're actually meeting the requirements of the problem. So what's going to happen is I would make a copy of this value onto destination. I would call top and then push it onto the destination stack. And then right now, after I call this, we have 2 copies of that value 1. So in order to do this, I then need to pop off the previous stack. Does everybody see that? So now what I would like you to do, and this is going to be the last thing we're going to do for code, is I want you to go to line 24 in hanoi.cpp. And what that is going to do is we're going to show how to use recursion to solve this. So if you go to hanoi.cpp in source, and go to line 24, you're going to see that I have a source, destination, and auxiliary. So we have 3 towers and a number of moves. So what I want you to do is we keep going in this recursion. If n is greater than 0, then the first thing we would do is we're going to flip the source. So here we have source, destination, and auxiliary. So we're going to flip the destination and auxiliary when we go on our first recursive call. So you're going to say Hanoi, and we say n minus 1, source, auxiliary, and destination. Right? So that's going to make all the left recursive calls. Then we're going to call that move method I just showed you. So when we get to this middle place, what that's going to do is I'm going to say source and destination, because the recursion is going to tell me at that specific point which change I need to make. And then num moves. And then the right recursion is just going to be Hanoi n minus 1. And then what we're going to do is we're going to flip auxiliary and source. So it's going to be auxiliary, destination, and source. And that's it. This is the benefit of, one of the benefits of recursion, is that we can take complicated problems and simplify them. So what I'm going to do, because we're now at 2 o'clock, is I'm just going to compile. And how I'm going to start next lecture is I'm going to go through the animation in detail of how recursion and the stacks are being used to solve this problem. So if you have it working, what you should be able to do is run make Hanoi. And what did I forget here? Oh, I need to add, both of these I need to pass num moves. My apologies. And do the same thing here. So when I update it and compile it, and now I have it working, and then the way to make it work, you do exe, Hanoi, and then what I'm going to do is I'm going to do 3, and that represents 3 plates. I'm going to go over in more detail what that represents in next lecture, but we see that I have 7 moves. And if I do 15, we see that 2 to that 15 power minus 1, 32,767, gives us the correct, most efficient answer. So you can review my video. You can get this submitted by Friday night. Good faith attempt counts for full credit. Coding Challenge 3 is not due until Saturday at noon. And the reason I did that is because I know you all have a systems programming exam tomorrow. So I wish you all the best of luck on Professor Bowie's exam. I'm not confident you're going to crush it. And on that note, it's 2 o'clock and my time with you is done. You are dismissed. And I will post Coding Challenge 4 tonight.